So yeah, we've run the model for what have we done? We've run the ACCESS ESM 1.6, or at least some kind of preliminary version of it, for 650 years. So what you're seeing here is all the output in the directory where I'm running it, the archive directory. And all this output has been saved. I think Arnold Sullivan pointed out that we have something like 2.5 million netcdf files, which is causing some problems for some people. But you know, these things are expected when you're starting up a run, and yeah, we're doing the best we can. So I'm going to present today from within my own wheelhouse, which is really the ocean, acknowledging that the major changes so far have been to the ocean in this version. So we have Wombat Light Ocean Biogeochemistry. That's coupled with the MOM5 and SICE4 ocean sea ice models, but with an important update to the iceberg redistribution of fresh water by Dave B. And the land and atmosphere changes are really to come in, who knows, like I'm not sure how long, but in the near future, I think those changes will be added. Yeah, soon. So those changes will be added in soon. There's a lot of activity with John and others on the emails. I mean, there's so many of them. And yeah, thanks to ACCESS-NRI for tying it all together in the 11th hour, helping us get there. So I'm going to talk a lot about the ocean, and I'm just going to give a pretty dry summary of what I see in the output. And maybe we can just discuss as we go. And if anything jumps out to you, just talk. So this is the evolution of temperature, global mean temperature and salinity from the ocean. So there is a small trend. The ocean was losing temperature over the first 600 years of the run, and then there's been a slight increase thereafter. This is probably within variability though. The change is quite minimal. And as someone who runs ocean-only models typically under kind of repeat forcing or maybe doing hindcast experiments, this is my first go really with running Earth system models. This seems fine to me. I'm not sure if it makes any alarm bells jump out at anyone else.
Pearse, I'm sorry to interrupt. It might be good to highlight that there were some changes to the code and parameters at the beginning of the run, so that might explain some features, but that we have a continuous kind of period, the last 200 or 300 years, where there are no changes to either the setup or the model. Is that correct?
Well, there has been no changes to the physical model. So this is a continuous run of the physics with no changes to its parameters or anything.
So only relevant to the BGC later.
Yeah, it's only relevant to the BGC. So really we have something like 300 years of continuous run with a BGC model that hasn't been altered, but we have 650 years of continuous run with the ocean physical model. Don't be confused by the 700 here. It starts from 100, so that's the 650 years. Salinity, there's a constant drift down from salinity. Maybe this relates to something, Ian, you've been seeing, where the ocean is losing fresh water.
So if we get time at the end of this meeting, I will show you updates from our latest runs, and it's different.
Okay. Moving on. Okay, so this is the evolution of temperature and salinity in the surface. So really, we're losing heat from the ocean, but it's not really having an effect on surface temperature. And surface salinity has been trending down a little bit as well. But coming out to something that looks pretty stable though by the end of 650 years. This is the total mass, volume and mass of seawater in the ocean, so it's trending up. I suppose if the ocean is losing fresh water, I can imagine how the mass of seawater is increasing. but and maybe, well, we're losing heat slightly in total. So there's also an increase in volume. So I'm not sure whether this rings any alarm bells. But or is this normal?
Yes, I don't think you're losing fresh water. You are, I mean, your salinity was decreasing, it was not increasing, right?
Sorry, yes, it was decreasing.
Yeah,
Yes,
so I mean, it
yes.
goes in the same direction.
Yeah,
whether
so it goes in the same
correct or
direction. That's
not,
right.
It's
That's right.
a question, but it goes in the right direction.
Okay, good. That's true. Thanks, Laurie. Okay, great. Okay. So this is my attempt at creating the total heat flux budget. There's a lot of variation per year, but this is sort of the average over 10 years is the red. So there's a constant, I'm not sure whether the output is calculating it correctly, but seems like there's a constant but slightly positive flux of heat into the ocean, and the formula is the heat fluxes from P minus E, long wave, short wave, sensible, frozen precipitation, runoff, and evap. I was confused about why there's an evap output as well as a precipitation minus evaporation. I figured that would be folded into the P minus E. But if I take away the evap, it becomes something like positive 40 petawatts. Yeah. So anyway, this is why I've got a little question mark here. The salinity fresh water flux appears to be pretty balanced. So that looks right on. But this is normally outputs that I would typically look at, right? So maybe some of you are more familiar with this kind of diagnostics. And I'll take that as maybe I should just move on. Okay, Martin. You're mute.
That the heat flux is positive, but the 3D temperature is going down.
Yes.
I would have thought it was going up.
Yeah.
So to answer on that one is that we do have a negative top of the atmosphere radiation balance. So and we also have something weird in this run going on the land. So we have to be a little bit careful. I think we've got a heat sink going in. I think we've got a heat sink, but we're still not fully balancing the ocean net radiation balance at the moment. So it's still cooling as a whole. But
the ocean itself should be consistent, I think.
Yeah,
but
I think you're probably right.
It's pretty small. I think if we compare to ESM1.5, I think that's pretty close to.
It's more or less the same.
Is it not?
I think so.
Sorry, is it not accounted for by some sort of latent heat flux from the freshwater accumulation?
Well, that would be in this. It should be folded in with this P minus E. I would.
Yeah, I'm a bit puzzled why you've got all this F-frac runoff and evap and P minus E terms added into the heat flux. I mean, obviously, yes, there is one latent heat term, but I'm puzzled why all of them are there.
Well, I took out. Well, this is frozen precipitation specifically.
Yeah.
So that's not actually associated with. It's like, I guess it's the cooling associated with, say, hail,
Yeah.
right? But yeah, this isn't normally things that I would look at. Evap, I feel like you're right, Siobhan, it should be folded into P minus E, but I got a value closer to 0 by including it. So
it's a bit of a strange one.
yes, maybe we should just move on.
I suppose just comment on the units there. I mean, you've got petawatts, so that's for the globe, right? So if you convert that to per meter, we're down to what, point a bit of a watt per square meter. So how's that compared to the top of the atmosphere imbalance? We're getting close to those same small numbers there. So yeah, the reanalyses do not balance. So yeah, it's small.
And you have to remember that you never actually know the temperature of the rain and the precip at all. So this is actually not possible to actually fully account for all of the fluxes that are going on.
Okay, interesting.
Because the rainfall just rains.
Okay.
You don't know what temperature that rain is, or the temperature that snow is.
Oh wow. Okay.
Or at least
All
you
right.
don't on the land.
All right. Well, who wants to see some BGC? I do. Okay. All right. So we can circle back to this at the end if people really want to talk about these things. But I wanted to show everyone the carbon cycle, the evolution of the carbon cycle and nutrients. So, and the ecosystem state. So what you're seeing here is we're going to start with carbon. It's a thing that most people care about. So we're going from year 400 to 750. This is 500 to 750. So this is in actual output files, it's output 400 to output 650, right? So it's 250 years of continuous BGC integration and then the reason why I took 400 was because 50 years before that is when I altered the BGC model and fixed a bug and tried to reset some of the fields to scrub out the effect of that bug, which was at year 352. So now this is 250 years of continuous BGC integration with a model that's consistent. So what you're seeing on the left is the continuous concentration, average concentration of carbon in the ocean. These numbers look pretty good. On the right is the trend. So this is the change per year going up and down. So you see the full seasonal cycle, but then I've also in the red and the green is the average change averaged over 1 year and 5 years. So it's trending down towards zero. And you can kind of see that it looks roughly linear at the beginning, and then it sort of starts to come down a little bit, but we still haven't reached steady state with the carbon cycle. And to be honest, the carbon cycle takes roughly 3,000 years to come to steady state in ocean models. So that's not surprising. What's useful to look at though is the rate of change. So if I look at this rate of change and then I extrapolate out for 1,000 years, it's roughly 13 millimole per meter cubed on average around the global ocean per 1,000 years. If you look at the actual values of carbon in the ocean, this amounts to roughly a change of 0.5% of the inventory over that 1,000-year time period, which means if we run the model for 3,000 years, we get maybe a change in total carbon of 1.5%, which I think is quite a good result. So it means that we don't have to worry about, at least in terms of the carbon cycle, losing too much or gaining too much over our spin-up run. The same thing can be said for alkalinity. Alkalinity is also really important in the global carbon cycle. There's a slight loss of alkalinity, which is trending down towards some constant rates, and it amounts to roughly 0.85% of the inventory over 1,000 years. So this will be, this isn't too much of an issue. And the reason why we are losing alkalinity from the system is because we now in Wombat Light, we now have burial. So we have a loss of alkalinity through calcium carbonate fluxes out the bottom. And we do try and sprinkle back that alkalinity over the surface ocean to account for that. But the calcium carbonate cycle also responds dynamically. And so, yeah, it's adjusting. But the adjustment isn't so extreme as to cause us any worry over the life cycle of the spin-up. And so this is the alkalinity field at the surface. So on the left is the model, and on the right are the OBS. And apologies for slight difference in the longitude wrapping here. So on the right, the observations go from the southern tip of Africa all the way around to the southern tip of Africa. And then here on the left, the model is, you know, just shifted a little bit. But you can see where there's high alkalinity in the OBS, we get high alkalinity in the model, and vice versa, the opposite as well. Low alkalinity is where we get low alkalinity in the OBS, although there's some places where maybe there's a little bit of a lot of fresh water coming out, but we don't have any riverine fluxes in this model. We haven't turned them on. So that could be something we play with, but again, it would be something that we'd need to consider and get everyone's advice, because I think if we start playing around with rivers, then we change these rates. I've already got burial on, permanent burial, and if we add rivers, then we start changing these rates again, these rates of change and percent changes in inventories. But overall, looking okay. No red flags so far.
Pearse, right?
Yeah.
You just go, yeah. So I just hadn't noticed this before, but there's no Gulf of Mexico in the one ESM model?
No,
sorry,
there
Gulf
is.
of America, I should say.
Gulf of America. There is in the ESM on the left. These are the
Oh,
OBS on the
sorry.
right. Yeah.
I see the OBS on the right.
OBS on the right. Yeah.
Please never say Gulf of America ever.
It's a joke. Yeah, obviously.
Where's my red cap? Anyway, okay. So the nitrates, we're losing nitrate out the ocean. This is also due to this burial term, but again, nothing to be worried about. It's roughly, you know, a loss of 0.3 millimole per 1,000 years on average. So that's roughly 1% of the inventory over 1,000 years. This maybe we could think about adding another flux of nitrate via the rivers that would change this. Much like the alkalinity, right? If we added riverine fluxes of alkalinity, this constant loss would end up being a little bit more of maybe a positive, near positive. Where are we losing nitrate? Well, there seems to be a shift, quite a significant shift, and of nitrate from the top to the bottom of the ocean. So this is just a random section through the Pacific at 230 degrees east. So that's like dead in the center of the Pacific Ocean. And the blues mean that we've lost nitrate, and the reds mean that we've gained nitrate. And this is comparing years, the final part of the simulation with the first part after the bug fixes. So either this is a long-term shift in physics, or it's a long-term shift in BGC through sinking processes and productivity processes. And I should probably look more deeply into that to figure out what it is. But it looks to me like an upper and lower overturning cell thing, or it could easily just be a shift in the amount of organics that are reaching the bottom versus the top in terms of the sinking of those organics. Oxygen is a little bit more dicey. Okay, so we've lost roughly 12 micromole of oxygen over the course of the 250 years. This rate of change amounts to roughly 41 micromole per 1,000 years, which is equivalent to roughly 25% of the inventory. That I hope would balance out soon, but it doesn't look, it looks pretty linear to me. So this might mean that I have to go back into the code and alter some of the parameters around oxygen. That said, though, it could also be, I mean, oxygen is very much a physically dominated tracer. It is affected by BGC and by biological processes, biological demand, but it's very sensitive to the physics. And so maybe there's some kind of long-term shift in the lower and upper overturning cell.
It's funny.
I couldn't hear you. Oh, okay, I'll continue. So I suppose one of the big changes that's happened to the physics in the simulation, right, is the freshwater fluxes being distributed not at the Antarctic margin, but over the Southern Ocean with the sea ice change, right? So it's possible that those changes in this model, which were restarted from, they were restarted from, I think it was a warm start, right, from the ACCESS 1.5. So there may be some changes in the physical system that are causing a redistribution in the upper and lower cells and having a big impact on the oxygen. And I guess that goes hand in hand with this redistribution of nitrate as well. But it's something that I need to look at.
Yes, do you have the oxygen distribution changes or not?
No, I didn't quite get to that. I could once we go into a discussion after this, I can plot it up and then share it with everyone.
Make a couple of quick comments on that.
Yeah.
I mean, yes, there is some change in the overturning with the redistribution of fresh water. So the Antarctic bottom water does look a little bit stronger, you know, about 10-20% stronger. Not hugely, but there's a small change there. So, so there will be some impact on that, and likewise on your heat content. I'm not surprised that that it's changing somewhat there. But then, yeah, in ESM 1.5, oxygen was an issue, and I attributed that to how we were handling when oxygen went to 0. So we had the remineralization taking oxygen out of the water column. So I'm not sure what Wombat Light is doing at the moment when it consumes all the oxygen. What then happens? Does it just stay at 0, or does it go negative? Do we have negative oxygen concentration? So anyway, there were some issues about how that was handled. So we had some funky oxygen results in ESM 1.5 because of that. So
yeah, I might need to look at that again. It's a good point. It's a good point, Matt.
Yeah, that's all.
So you're seeing a spin up of the lower overturning cell?
Well, only by in the overturning calculation. So it's very noisy. It's noisy on a range of time frames. There's interannual variability, decadal variability on that, but it does, on the long-term averages, there is more bottom water, Antarctic bottom water in the new experiments compared to the old experiments, which Dave B was expecting. So
okay, that would also explain this as well, a shift of nitrate into the low overturning cell of that spinning faster. Yeah, okay. Okie dokie. We have a little bit too much iron in the ocean. This was a bit of a surprise for me because I'd done a lot of work on the iron cycle. So the iron content is roughly, for those who are familiar with iron, it should be roughly 0.6, 0.7 nanomolar. And currently we have roughly like double that in the deep ocean. The trend is slowing down quite significantly, but these values, so this is sort of a again through a profile through the ocean, just a section, a latitudinal section. And really iron should be less than 1 more or less everywhere outside of directly above a hydrothermal vent. So the fact that it's high everywhere, I think this probably stems though from the bug fix, and it's like a hangover, legacy hangover from the errors that in the BGC code that happened before. The nice thing though, if I skip forward, is that even with a lot of iron in the deep ocean, what I'm showing you here is nitrate on the left, surface concentrations, and dissolved iron on the right. Iron is still quite low in the surface ocean, so the phytoplankton are constantly stripping it out. And we still have iron limitation. Red's are iron limitation, and this is the annual average, and blue's a nitrogen limitation. If you look at the OBS, red here means iron limitation and blue means nitrogen limitation. You can kind of see blues and co-limitation of nitrogen with iron is in the oranges. Blues and oranges exist in the gyres, and then iron limitation exists in the Southern Ocean, the subarctic seas, and the equatorial Pacific. And we're getting that in the model, which is nice. This is an annual average, of course, doesn't really tell the full story because iron limitation is strongest in the summer. So this is the austral summer now, and you can see that iron limitation really picks up in the Southern Ocean. So even though we have too much iron in the model, the new iron cycle seems to be doing an okay job representing iron limitation in the places where it's meant to be limiting. I will go backwards and finish off the global rate of change. So we have now a look at the organic carbon in the ocean, and it's trending down somewhat. And this is consistent with something that Matt was finding, is that net primary production in total has been trending down over the course of the simulation. This is consistent with the movement of nitrate from the upper into the lower overturning cell. And this is just an image of the change in nitrate in the surface ocean over that 250-year period. And you can see that it's being pulled out of the upper ocean and put into potentially this lower overturning cell. And that's consistent with a decline in productivity on the right, more or less everywhere in the lower latitudes. So this is a problem. Our productivity is not too low. It's roughly 35 petagrams of carbon per year, which is on the lower side of the observational estimates. It's maybe at the very lower tail of sort of a box and whiskers distribution that you'd expect from the obs. So it's not outside, but it's getting close to being outside of the obs. And so maybe we might be putting too much nutrient in the lower overturning cell and taking it out of the upper ocean. That said, our phytoplankton chlorophyll looks pretty good. So this is phytoplankton biomass on the left, which is in units of carbon, and this is in units of chlorophyll on the right. And it looks very similar to many people, I suppose, but there are slight differences associated with photoacclimation due to high light or low light. You'll notice the peak in chlorophyll is a little bit further south than the peak in phytoplankton biomass in the Southern Ocean. And then this sort of tongue of high phytoplankton biomass that pours out in the equatorial Pacific is a little bit tighter due to high light conditions in the equatorial zone. And it looks, these are the observations, same units, looks okay. I mean, I feel like when you're looking at obs of BGC, you have to be okay with squinting your eyes and blurring everything and just being like, okay, well, similar distribution. So there you have it for phytoplankton chlorophyll.
Hang on, Pearse. Sorry.
Oh, yeah, sorry, Laurie, go for it.
Yeah.
Yes, sorry, because I have to go. First, I want to congratulate you for your work. It's great to see that. Great to see improvement. I was just confused as, I mean, you say the organic matter and the nitrate direction go in the same direction, right? I mean, you have accumulation of nitrate in the deep ocean, you have reduced export production and reduced organic carbon, so that goes in the same direction. But you also have reduced oxygen, and that's what is bugging me. I mean, also if Matt says that the lower overturning is strengthening, I'm just so I'm just saying the oxygen doesn't seem to fit with that story. And should I say they're a bug?
It's a good question. I feel like yeah. So if I was going to look at this more deeply, which I will immediately after this meeting, Matt's comment about the negative oxygen in the low oxygen zones, potential cause of what you're looking at. The other thing is just age, right? Like if the residence time of the ocean is decreasing,
but
you
I
can
said
have.
It was... Oh yeah, okay.
Sorry. If the residence time of the ocean is increasing because you have some transient change in the ocean overturning circulation, then you can have a situation where you trend down in your export production and your biological production, but at the same time consume more oxygen. So
yeah,
so it's possible that's the case
it
too.
was accelerating. That's why I was confused. I mean, I would expect increased oxygen in the deep ocean if your lower overturning cell strengthened, but
yeah, I guess I would too, but it's possible that I haven't looked at ventilation age, and that's something that I will do immediately as well.
25% is quite a lot, right?
It is a lot, and it's something to be concerned about. Yeah. So
sorry, I don't want to bother you with this.
It's true.
I can't imagine how challenging that is. It's just, yeah. Anyway,
I think
sorry to
maybe.
interrupt, and I'm gonna have to run. So.
Okay. All right. Thanks, Laurie.
See, something that might tie in there. So ACCESS ESM 1.5 had an excess of oxygen deep in the Southern Ocean in the relative to observations, and with your retuning of Wombat's light, that's not as bad. You know, sort of there's not the same build-up of oxygen in the deep ocean. I mean, I suppose we need to be careful there. We've only run it for a couple of 100 years, but you know that's looking better. So if we have a better boundary condition from the Southern Ocean, that could be changing things, and that's going to propagate through the rest of the ocean volume. So yeah. Anyway, there's few things that could play out there.
It's possible as well. The bug that I corrected halfway through this run was a bug that caused an excessive accumulation of detritus in and near the sediments. Okay. And when I altered the restarts, I'm pretty sure, to change the alkalinity, the carbon, the nitrates, but I may not have changed the detrital accumulation, like considered the excess detritus that accumulated in the sediments, because we hold on to a sediment pool of organic carbon. And if that was 10 times what it's meant to be, then what will happen is by remineralizing that carbon, you're constantly pulling oxygen out of the deep ocean. So that's maybe what's happening. And I think that's the cause of the excess iron as well, because there was a lot of excess iron that had accumulated in the sediment. So I may just need to nip that in the bud, and then maybe oxygen will.
Did you reset oxygen there as well?
I did, yeah.
Okay.
I mean, the first thing is to plot actually the maps of anomalies, right? Because if you have oxygen, if you lose oxygen from everywhere, or if you just lose it from your bottom, that would give you a clue at what is going on.
Yeah. Okay. I'm going to do that immediately after this meeting. Cool. Thanks, Laurie.
Thank you so much, Pearse. Thank you.
Thanks. Okay. And I just wanted to, so this is the last slide. Hold on a second. I'd like to access the camera. Okay. Can you see that?
Yeah.
Yeah. Okay, great. So these are the CO2 fluxes. Top is the model. Austral summer on the left. So that's Southern Ocean summer. Austral winter on the right, Southern Ocean winter. And this is the model, right? It's the pre-industrial CO2 at roughly 280 ppm. Is it 284 point something? Is that the typically? But anyway, it's around 280. And what I've taken is a Copernicus product on the bottom, which is austral summer on the left and austral winter on the right. And of course, you know, our CO2. This is a machine learning estimate of CO2 fluxes, so take it with that grain of salt. Then also the fact that CO2 in this product, this is of year 1990, is 353 ppm, right? So you'd expect a lot more downward flux of CO2 into the ocean in these bottom plots than in the top plots. But nonetheless, the spatial patterns should be similar. That's what we want. We want similar spatial patterns. So a good correlation, but accepting some error. And I think encouragingly, we have a CO2 flux going into the ocean in the southern ocean during the summer. I think if you bump this up 70 ppm, you'd see a stronger response, consistent with the OBS maybe. In the winter in the Northern Hemisphere, we are reproducing this sort of hole of CO2 outgassing in the subarctic Pacific, which is nice to see. Less so in the North Atlantic here, we just sort of have this broad swath of ingassing due to temperature, due to cooling in the North Atlantic. And then in the winter, we see a similar pattern to the OBS, although excess outgassing, which again could be just associated with the fact that we're at a CO2 concentration of 70 ppm less than the OBS in this case. But encouraging signs, at least in the CO2 fluxes, that we're reproducing some of these patterns, which is nice to see. So Yeah, that's all. And I definitely need to look at oxygen and age and overturning.
Thanks, Pearse. That was a really nice, comprehensive summary of what happened in our first kind of long spin up of a pre-ESM 1.6 version. We already answered questions while you were giving the presentations, but are there any other questions for Pearse? Looks like we covered everything already. You already outlined what the next steps are, Pearse. Just for everyone else, the plan in terms of going forward with our before I can do that, I hand over to Aidan. You have a question?
Oh, no, I just had a shared a question just to make sure that your presentation will be uploaded to the notes on the forum, right?
Yeah, I can do that. I might actually,
cool.
while you talk amongst yourselves, because I will, Aidan, did you have your hand? Oh, you had your hand up?
It's gone.
Okay, it goes gone. Yeah, so I'm actually just going to plot oxygen now.
On the fly.
On the fly.
Yes.
Yes.
Thank you. I can keep talking a little bit.
Okay.
While you do that, if that's okay.
Yep.
Just for everyone else, what our plans are with continuing the spin up for ESM 1.6. You have seen from Pearse's presentation, carbon cycle takes a long time to spin up. Estimate is 3,000 years. That's certainly in line with what we experienced with the ESM 1.5 for CMIP6, but also noting every time we implement a change while we're running the spin up, there might be some reset required, and that might increase the time. With the ESM 1.6 version expected to be slightly faster than the ESM 1.5 release, this should be doable for us to get at least closer to where we are right now. I think at the moment with the test runs that have been done by the NRI, we get over 20 years per day, roughly an hour of run time for the model, which is great, and every little bit here helps with those long spin-up simulations. The plan is to bring Pearse's version that you have seen today together with the changes that happened or will happen on the land side fairly soon. Ian is kind of looking at a few things at the moment, a few things to double check, a few choices still to make, but we are hoping that fairly soon, and I'm not putting a more definite timeline on this, we will join these two development streams, making use of the spin-up that Pearse has done already and the model changes that have gone into the code, and then starting a new spin-up. And we're also expecting that we will run with this new spin-up some choices in parallel to test various configurations. The biggest change that happened recently is around our vegetation. Our pre-industrial 1850 vegetation map has changed by quite a bit, more in line with the LUH3 dataset, but also that's not finalized or released yet for CMIP7. It's all the kind of CMIP6 plus pre-release, but we are running test runs with those new vegetation fractions as well already. So as I said, the plan is to bring these two together, start a new spin up, and then go from there. And then maybe in 4 weeks or whatever the time frame is, we will be able to provide an update on that, maybe more focused on other areas as well. That could be more atmosphere focused or land focused, depending on where we are at and where the interest is for this community as well. I guess what we would like to achieve in the meantime is to, we already talked about output at the beginning, to get on top of providing outputs through post-processing that we can then plug in directly into other evaluation tools as well, such as the ESM tool, iLamp, or the Ocean equivalent. So that is separate to the summarization process for CMIP, or at least I think it is. And Pearse has some slides up now. Do you have any questions with what I just said, or any clarification required? Otherwise, I hand over to Pearse again, just noting we have 5 minutes left. I can't see any hands, no one is speaking up. So maybe I quickly hand over to you, Pearse. Another maybe 2 minutes, and then we need to wrap up to ensure that we finish in time.
Okay. Yeah, so I just looked, this is oxygen change on the left, and this is age tracer. Thankfully, that was turned on. So the oxygen tracer here, you're seeing a big decrease. It's consistent with what happened with nitrate. Big decrease in the deep ocean. Don't be fooled by how light these blue colors are. The scale is to 80 micromole, which is roughly, like it's a lot of oxygen loss. So you're seeing roughly 40 micromole to 30 to 40 micromole lost in the deep ocean. And this is the age change. So this is in the Pacific. So this is a general increase in the age of the ocean over the course of the simulation by about 260 years. And given that what I'm looking at here is a difference between the 200 and I'm taking a difference over 250 years. So from year 400 to year 650, essentially this isn't being ventilated. And so there's not really waters being mixed down, which is actually maybe a concern. And where is my other? Here it is. Okay, here we go. So this is at year, sorry, this is at depth 3,000 meters, and this is the change in age. So yeah, the deep North Pacific is not being, it's really increasing significantly in age, but okay, maybe this is just because the age tracer started from 0. That's possibly, that's very, very possible. Yes, that's very possible.
Age tracer isn't spun up.
Yes, age tracer is not spun up. Okay, so we're losing oxygen from maybe the age isn't useful at the moment because it's still spinning up. The oxygen tracer is, however, useful. So I think we've lost quite a bit of oxygen from the deep ocean. I'll look into that as to whether it's to do with the BGC bug. It's very possible that it is. So I'll report back. Ian, you're muted.
Do you want me to show you what's happening to the salinity with the new land?
Yeah, why not? Yeah, definitely.
Ian,
okay.
While you get this up, I will just ask the question, is there anything else we would like to raise? Any other business, anything to be aware of? Just while Ian is getting the slides right. Yeah, David?
Yeah, look, I just want to mention, I've had some preliminary discussions with Pearse about trying to apply some acceleration methods to the Wombat tracer spin-up. So there is this algorithm which has recently been published, which can potentially spin up tracers a lot faster just by interacting with the restart files. Okay. I've tried it for age tracer. It works really well for age tracer. I have a plan to implement this for a Wombat configuration that Pearse has shared with me. I've been a bit sidetracked the last few weeks, but this is definitely something that's on my radar. So hopefully Pearse and I can chat further about that and come up with at least a trial method of speeding up some of these spin-ups.
That sounds great. Thanks, Dave. Just a reminder, our next meeting is on the 13th of March, and I will hand now over to Ian.
So I had tried to keep things really short here. In parallel to Pearse's long run, we've been doing a number of development sides from the land atmosphere side. Results here for the rate of change of the ocean mass, total river inflow, average surface temperature going across, average ocean volume temperature, and the average ocean salinity going from left to right. Blue is the Pearse's run. Orange is a run from that we started using a version of cable 3, and then the different rows are dependent on whether we've added the green is whether we've added science fixes in or we've changed the land use, land cover. What basically has happened is that one of the things I've picked up there's some quirks around what was happening with some corrections going on to the interchange between runoff into the river scheme and then out, and addressing those has meant that we actually end up with a much more, at least over the first 50 odd years, we've got a much more stable salinity. At the compensation for that, we've actually got a slightly bigger loss of energy from into the ocean, a bigger loss of temperature of the ocean. So I don't know whether that makes will make a lot of difference for the results that Pearse is showing, but we certainly seem to have, by luck, I think, actually managed to address that long salinity drift that we had in ESM 1.5 and the earlier runs.